Hello and welcome to today's webinar. This is Mark Plantier of Enercon Industries, and we're pleased you have joined us for today's presentation. Which surface treatment technology is best for my application? Corona, plasma, or flame? You may ask a question at any time during the webinar by using the GoToWebinar question tool. We'll reserve time at the end of the webinar to answer your questions. Today's webinar is being recorded, and you will receive access to the recording as soon as it's posted online, usually within 24 hours. In today's presentation, we will address a common question we receive from converters and extruders alike. Which surface treatment technology is best for my application? We'll begin by looking at the purpose of surface treatment and how corona, plasma, and flame technologies are similar and also uniquely different. We'll look at variations within each technology category and review considerations you should keep in mind when implementing a corona, plasma, or flame surface treating system. You'll also get insights on common applications and how these applications are best served by each technology. Ultimately, you'll see that the key details of your application will lead you to the best technology choice for your operation. Enercon is in a unique position in the industry to respond to this question. Which technology is best? As we are the only company that offers corona, plasma, and flame technologies. In addition to our field application experience, we also offer lab trials that allow clients to put their application to the test across all three technologies. Today, we're very fortunate to have one of the leading experts in the industry on surface treating technologies and applications. Tom Gilbertson is Enercon's Vice President of Application Engineering and has over 35 years of surface treating application experience. Tom works with converting and film extrusion customers on a daily basis to optimize their surface treating operations. Tom is a frequent presenter at industry events and has written numerous technical articles on the topic of surface treating. With that, Tom, I'll hand the presentation over to you.
Thank you, Mark, and welcome everybody. Happy New Year. I'm glad you're able to join us today for this discussion about what surface treatment technology to use, and look forward to your questions and comments as our presentation goes forward. So today, as we indicated, we're going to be talking about optimizing adhesion with surface treatment, and as Mark indicated, we're really dealing with the three main types of surface treaters: corona, atmospheric plasma, and gas flame. So with that set up, the question always becomes, why are we treating these films anyway, right? What's the purpose of this? Well, if you're not familiar with surface treatment and you're attending this discussion maybe for the first time, you kind of already know the answer to this because we've all done this before, right? And so let me explain. We take up like a little plastic bag out of our pantry because we're going to put something in it. We have a handful of hardware, maybe we have some leftovers, whatever it is, and we put it in the bag and we seal it up, and then we say to ourselves, if I don't put some information on the outside of this bag, I'm not going to remember all the details I want to remember in the future. Maybe you want to write a date on there, maybe you want to put some information. Well, if the bag that you chose to use doesn't have a little printed stripe on it so that you can write on it, but you just try writing on the bag itself with a marker, you've already experienced this where the marker doesn't wet. You just can't get the ink from the marker to thoroughly wet the surface. And what that means is the surface of that bag has really low surface energy, meaning that the surface energy of the bag is at a lower amount than the surface energy of the solvent ink that's in the pen. And so when you try to write on it, that ink doesn't wet. It not only doesn't wet, but it doesn't stick either. And that's because plastic films, polyethylene, polypropylene, polyesters, things of that nature, they all have a very relatively low surface energy or dyne value. And that's sometimes it's because just of their inherent value. Sometimes it's because there are surface contaminants that come to the top. In my example of the bag, those contaminants usually are migrating additives, slip additives that come to the surface. And you might ask yourself, well, what are those there for? Why would why would the manufacturer put these additives in the product to make it slippery? Well, the reason for that is there's numerous reasons for that, but the main reason is they want you to be able to open the bag. They need the bag to be able to easily open. All right. Again, this is an experience you've probably already had. If you take a trash bag out of your pantry and you're going to replace it in the kitchen, your kitchen receptacle, sometimes you get a bag that just doesn't want to open, right? It's difficult. You have to really kind of work at it to get the bag open. And that's because sometimes that's because the additives that are supposed to be in there to help that work aren't enough. You know, they're not enough in there. So they have those additives. The surface of those products is just such that it just has a very low surface energy, and it's hydrophobic. It just doesn't want anything, any sort of liquid to wet out and stick to it. Next slide. So you can almost look at it this way, right? We have these plastic films that we try to convert or that we manufacture, and they all come with a certain amount of this baggage that's just inherent with the film. And like I said in the previous slide, that baggage could be additives in the film, could be just the chemical nature of the surface of the film, could be, in the case of converting, it could be the age, you know, how long was that roll of film in storage, you know, things of that. And so all that baggage has to be accounted for. Somehow we have to be able to take that surface that's got all these imperfections, if you will, in it, and we got to clean that up. We got to get that surface sorted out so that we can print, coat, laminate, you know, convert it. We got to do something with that film. So one of the ways we can do that is through a corona treater, as illustrated in this slide here. We can take that film that has all these things to them, and we run them through a treater, and the treater will clean the surface and increase the surface energy. So now the material is more receptive to an ink, a coating, or adhesive. Next slide. So this is a great picture and a great illustration of what I'm referring to. So in the converting side of our business, you can see what happens in this slide when you try to put down an ink or a coating or an adhesive on a surface that's not cooperating. So if you really focus on the image, the inset image in the lower right-hand side of the screen, you can see exactly what I'm referring to. So if you imagine these little droplets as, say, bits of coating or bits of adhesive, on half of that substrate, the surface is not receptive. So when you try to apply the coating, it just sort of beads up and rolls around on there. Sort of like, another example might be that you're familiar with, might be when you just get your car washed and waxed and it rains on it. Well, you're disappointed, of course, because you just got your car washed, but you noted that the water, the rainwater, kind of beat it up on the car and runs off the side of the car. And that's because your car with the wax on it has a very low surface energy at that point. And the water won't stay there. It'll just run off. When we treat the product, as again in this illustration shows, the liquid just wets. It totally wets the surface. And using my car analogy, same thing happens. You may have had sometime in your life an older vehicle that's been exposed to a lot of sun and oxidation, of heavily oxidized surface. And when it rains on that car, what happens to the water? It actually wets, right? It actually kind of spreads out on the paint and that oxidized paint surface. So really, surface treatment in its basic format is taking the surface of that substrate and it's enhancing it, cleaning it, and activating it such that a ink, a coating, and adhesive, something of that order, will adequately wet the surface. Next slide. So we have three basic technologies that we can use to do the job. You know, so when we take a substrate and we want to increase the surface energy of that substrate, there are three pieces of equipment that could be used to do it. Now, at a 10,000 foot level, they all treat the material. So without regard to the material itself, if it has a low surface energy and I expose it to either flame, gas flame, or I expose it to a corona treater of some design, or I expose it to an atmospheric plasma system, the chances are that every one of those technologies is gonna take the surface energy from where it is and increase it accordingly. However, that's a really high level view of it and not really accurate when you get down to a closer view to see what actually is the appropriate piece of equipment based on what you're doing. Next slide. So again, from a overall umbrella sort of view of this, the specifics of your application really will determine the technologies that should be used. I get the question all the time, you know, what is the best surface treating technology? I only want the best one. And of course, that's a common thing, and it makes, you know, at a certain level, it makes sense, right? Who wouldn't want the best piece of equipment for a given application? But the details of your application really do shape which direction and what piece of equipment we're going to use. And a lot goes into that. As you see, as we go on, we look at a lot of things. We look at all the details of your application. We look at your budget. We look at where the system is going to be located. There's a lot of things that get kind of thrown into the pot and stirred around in order for us to come up with the right answer for you. Next slide here. So let's start with sort of the grandfather here, or the most common device that's used for enhancing the surface tension of films, and that's a corona treater. So corona treaters come in all sorts of variants. They can come in different styles and sizes and shapes, but at the end of the day, they're all kind of the same in that they all ionize air. Corona is just that. It's the method of taking high frequency, high voltage energy and ionizing room air. And that's really what a corona treater is. Now there are different designs and there are different pieces and bits of corona treaters, but if you again make it sort of simple for yourself, all corona treaters ionize air. That's what corona is. And the process increases the surface energy of low energy films. So we take a polyethylene, let's say, and we run it through the corona treater, and we go from an inherent dyne level of, let's say, 36 dynes, and we can easily get that substrate probably up to 40 dynes, or maybe even 42 or 44 dynes. Now, to give you some context here, most converting inks and coatings will operate just fine. They will wet and adhere just really well, you know, at a dyne level in that 40 to say 44 dyne range. So we don't necessarily need to treat the film to some extraordinary level. We just need to get it from its inherent value, what it is when we get it, up to an area that's more commensurate with whatever the liquid is. Corona treaters are very effective for all converting processes. So whether you're printing, coating, laminating, whether your solvent technology is solvent, or whether it's solventless, or whether it's UV curable, or whether it's E-beam curable, whatever it is, the corona treater can effectively treat the substrate prior to it going into your process. Thirdly, the treaters are very budget friendly. I mean, when you contrast and compare a typical corona treater to our two other friends here, the gas flame treater and or an atmospheric plasma treater, when you look at the bang for the buck, corona treaters offer a lot of value in that regard. And then finally, the corona treater doesn't affect or doesn't have a negative impact on the overall substrate functionality. You know, one of the questions we get from people sometimes is, hey, I have a high slip film, it's going to be used in a packaging application, so I need a particular COF, coefficient of friction, value on the surface. If I treat that film, is it going to screw up my COF value? And the answer to that is no. The corona treater is going to be sized and utilized in such a way that we're really just going to affect what we need to affect to get a good converting outcome, and we're not going to affect the underlying functionality of the plastic film. Next slide. So here are some of the considerations, and I just sort of, you know, picked the high spots of these. There are others, but the main ones does your entire web require treatment? So, or alternately, is the product that you're treating only need treatment in a certain area? So where are we driving? What's causing those two questions? What does that mean? Well, practically what that means is if I ask you that question, you say, yeah, I have a 54-inch web, but I really only need to treat the center 12 inches of it. So what that tells me then is we may want to choose a corona treater design for you that utilizes a selectable width electrode. So you can actually adjust the area of treatment based on the requirement. And the same thing for the next point, does it need selected areas of treatment? And so in that design where you have an electrode that can be adjusted, you can, on the same 54-inch web, you can set the electrode up so that you're treating 12 inches, and then you skip 12 inches, and then you treat 12 inches, and you skip 12 inches, that sort of thing, if that's the case. The third thing is a substrate conductive. Really important point, right? So if you say to me, hey, Tom, the treater's going to be on a printing press, and we run a lot of different jobs here, and some of the jobs we run have either a conductive layer to them, maybe it's a metallized film, maybe the product is a lamination and it's got some conductive components within the scope of the lamination, that sort of thing. Well, that gives me direction, because that tells me, well, if that's the case, if the product is conductive, I cannot use a metal electrode that has selectable segments, because the corona is going to arc to that metal. You're not going to get a corona, you're not going to ionize air, you're just going to get a lightning bolt and you're going to damage the substrate. So in that particular case, if the substrate's conductive, we're going to use some sort of insulated electrode, either a rectangular ceramic electrode, maybe a round ceramic electrode. It just depends on other details. Fourth thing is, is the corona process that we're talking about here, is it going to be used in a film extrusion or converting application? Again, very important. So usually in film extrusion applications, typically, not always, but typically, corona treaters use metal segmented electrodes and insulated rolls. Now that same treater could be used in a converting application, right? It could be. But if you go back to my comments about a conductive substrate, think about it for a moment. If you own this 10-color press and you have all these various materials come in your direction, different jobs that come in all the time, you're going to want the printing press to be able to manage all of that variation, meaning you want the equipment to be able to work with conductive as well as non-conductive materials, because, I mean, that's your business. That's what happens. You get all those sorts of products. Well, in that instance, once you tell me that again gives me direction. That tells me I can't really recommend a metal electrode system in that case, because your converting application runs metallized or conductive films, right? So that again tells me I have to use a ceramic type electrode, which takes us down a little slightly different path. If it's film extrusion, then I look at it and says, well, if it's film extrusion and you're making bags, like we started our conversation off with in my example, little adjustable bags. Well, if the bags are gusseted, or if the bags have certain features to them that treatment would be detrimental for, the only way I can do that is I would have to go back to a adjustable width or segmented style corona treater electrode, and that would be suitable then for a film extrusion application. So what I'm trying to get across to you all here is the details of your application, whether it's a film extrusion application or converting application, are really important to us, and they allow us to really give you some direction into the right piece of equipment. Although they all generate corona and they all do a great job, it's the way they're being applied and the usage there really dictate the style of the treater being used. And then finally, I wanted to toss this out here, this last comment out here, because I'm getting more and more questions over time here about ozone, and then the managing of ozone, as ozone is a byproduct of the corona process. When we have this discussion, you really need to come to the discussion with an understanding from your local environmental authority. Whatever authority in your geographic area manages this topic, you would go to them to get an understanding if, hey, can I just vent this treater outdoors, or do I have to put in some abatement equipment prior to venting outdoors? That's not a question I can answer directly for you. What I can do is I will help you, is I can help you understand how much ozone we generate, and the amount of it, level of it, and so forth, so that you can carry that information to this environmental authority of yours, and then the conversation can go from there. So that's just one other element to the considerations now that come into question when we talk about putting in a corona treater. So basic parts of a corona treater include really some pretty simple things, right? We have the power supply itself, that's connected to a high voltage transformer, and that transformer is connected to the electrode, which is mounted above a grounded roller. And in the case of our illustration here, we're showing a segmented electrode assembly, and we're showing an insulated grounded roller. The parts that you see here would change slightly if it was an insulated electrode, but by and large, it really would look pretty much the same. Next slide. So the options you have with corona treaters are a metal electrode, covered roll metal electrode, and that metal electrode can be fixed with, it can be segmented. You could have a ceramic electrode, which is basically a ceramic a bar, essentially, or a pair of bars that are housed and then mounted above a bare roller or a roller that has a conductive ceramic applied to it. The most popular corona treater of the three listed is the final one, and that's a universal roll treater. And that treater is used pretty much all the time in converting applications. So if you're printing, coating, or laminating, this universal treater, which has ceramic electrodes and a ceramic coated roll, is really the right choice for those applications. If you're in film extrusion, cast film, blown film, oriented film, many times you'll gravitate over to a covered roll system of some style. The bare roll, so that would lead you to say, well, wait a minute, where's the bare roll treater come in? So again, we have a home for those. If it's, let's say you're on an extrusion coating line and you have a secondary unwind that you're unwinding some foil and you want to treat the foil or clean it before it goes into a laminating process, a bare roll treater would be perfect for that, because the bare aluminum roll and the ceramic electrodes, the aluminum doesn't bother that at all. It works great for that. That's just one example that comes to mind. There are others. But as you can tell from my description here, again, your application details and what you're currently using and how your operations are really help determine whether it's a covered roll treater, a bare roll treater, or a universal roll treater. Next slide. So cover roll treaters look just like the picture shows here. This is a very common design that is used in film extrusion, sometimes mostly blown film, but sometimes cast film as well. And you can see the segments there where we can actually apply treatment just where we want it. Recently, I have the benefit to working with a client who has a 55 or 60-inch wide web, but they really only want to treat 12 inches. Now that 12 inches can move around on them. It's not always in the same space, in the same location rather. And so an electrode assembly similar to what's pictured here is great for that, because they can move that area of treatment to wherever they need along the entire 50 or 60-inch web width. The one downside to this, if you want to call it that, is it really doesn't work for conductive films. You can only use it for non-conductive. If you had a metal substrate that you tried to put through here, you would have a problem. The corona would just arc to you wouldn't get a corona. The electrode would just arc to the metal and shut the treater off, and you wouldn't be successful. So if you have a non-conductive, standard non-conductive film, these metal electrode systems work great for that. So up next are the bare roll and universal roll systems. They really share, their sort of twin brothers, so to speak, with each other. And they both have the same feature set. They provide very uniform and effective corona. They're suitable for everything, whether it's conductive or non-conductive. The universal roll sort of ups its brother a little bit because it has, depending on the material, you can get higher dyne levels with it based on the same output power as compared to a bare roll. It also has some benefits because of that ceramic coating that's on the roll. It really is a good insurance policy against things like reverse side treatment, backside treatment, any pinholing that may be potentially there. And if you have a very thin gauge film that could be prone to wrinkling, that substrate, that ceramic material on the backing roll is great for that substrate. Next slide. So I put this in this selection. I put this slide in this selection now to again just kind of cover the basics of ozone decomposers. As I just said, all corona treated equipment, a byproduct of generating high frequency, high voltage energy is ozone. That's just what happens. And so there was a point in time where many of us could just vent it outside. It wasn't a concern. But if you're in an area where that's not possible, then you have to look at one of these ozone decomposers. So a very high level simplistic view of how these work. They're not complicated devices at all. So we take the treater exhaust, we put it in the top of the enclosure. That airflow then goes through a particulate filter, think of a furnace filter in your mind, and then another bed, and that bed is full of alumina pellets. And then beneath that bed is actually the catalyst that does the decomposing from O3 to O2. And as that ozone-laden air is kind of put through that system, it comes out on the other end as O2 and a little bit of water vapor. And so it does a great job of eliminating the ozone that is created by the process. And from there, you can take and vent it outside. Next slide. So you can see here in this slide a picture of that ozone decomposer, but then also a couple of facts here. It converts ozone into oxygen and really eliminates the problem at the source. It can reduce the input level of treaters from around 150 parts per million to less than 1/10 of a part per million. And relative to standard sort of safety guidelines, that 1/10 of a million is defined as a safe level. Now, one thing to remember here, folks, even though you decompose the ozone through this device, you want to still vent that outside. You don't want to vent it in the building. And the reason for that is, while we do a good job of getting rid of the ozone, in all of our processes, we have other fumes and sources of things in the air that just get sucked into the treater. And so no one can really control those things, and at any given time we're not exactly sure what they are, nor are we sure of any reaction that may occur within the catalyst bed. Now, I'm here to tell you that fortunately I've not had any experience of anything negative there, but the fact is we just don't know. So rather than take that risk, we instruct people that when they put the decomposer in, on the exit end, you still vent it outside. Next slide. Here's just an installation overview so you could get a sense of how these are put into the system. So the key takeaways from this slide would be, you note that we have the ductwork coming from the treater, and it goes actually into a T there instead of an elbow. Many of you who have corona treaters, you may go out into your shop and say, oh, mine's got this big sweep in it. Well, when possible, we like putting a T there, and the reason for that is you do get condensation that can come down that exhaust pipe. And if I have a T there, I can put a clean out on the bottom of it, and rather than that liquid running back towards the treater, we can just have this drip leg and empty it right there, and it does a great job. Just a couple other quick notes on this slide before we move on. The ductwork we have here can be made from a number of materials. The preferable ones are things like Schedule 40 PVC, aluminum or stainless steel. The one material you don't want to use for this is anything galvanized. Don't use any galvanized material. Secondarily, if you have to use any material, any connection points that are corrugated or that flexible type ducting, really keep it to a minimum. I mean, a bare minimum. If I took that hard piping illustration out of this drawing, and I just put a big loop of corrugated ducting in there, it would be a problem, because the corrugated ducting is not smooth inside. You don't get a good airflow, a lot of turbulence. It's not going to do an effective job of getting the ozone out of the treater, and consequently a number of problems follow from there. So you want to use hard piping as much as possible. If you do have to use a small amount of corrugated material just for connection purposes or something, I guess that's okay, but you really want to keep that to a minimum. Next slide. Okay, so now we're sort of moving on from the corona treater topic up to the atmospheric plasma treater topic. So at this level, what I want you to know right now is that these two machines, a plasma treater, atmospheric plasma treater, and a corona treater, again, kind of twin suns here. In the corona treater example, we're ionizing room air, and that's what's creating a corona. In the plasma treater, we're providing a gas or maybe a series of gases that are coming from a tank farm that we have, in your plant, and we're bringing that mixture, that either single gas or mixture of gases, into the treater, and we're ionizing those gases. So from a simplistic standpoint, the corona treaters and plasma treaters are similar, meaning that they both ionize gas. The plasma treater does a better job at creating this sort of cloud of ionized gas with little to no filaments. And so does it matter? It doesn't give you, just because it doesn't have filaments in it, doesn't equate to a better treatment. It may equate to something better for a given film because maybe the film has got a very thin coating on it or something. And so if you had discharge that had filaments that could potentially damage that coating, well then, that couldn't, you couldn't use that. Then the plasma treater would be a good source for that. The plasma that we generate with a atmospheric plasma system is very dense, and it does a very good job at sort of cleaning the surface, providing a bit of an etching sort of characteristic to it, although this is all surface. We're not, again, we're not diving deep into the level of the material here. We're still dealing with, the top few angstroms of surface here. But it does do a good job at working materials that really don't respond to corona treaters. Next slide. So you can see here we have a plasma treater on this particular unwind wind in the image to the bottom right. Plasma treaters can provide higher treatment levels in some cases. They also can provide lower decay rates. Sometimes people talk about, hey, I treated this material, I got it to a given dyne number, a day or two later, the dyne level was reduced. Well, there's all kinds of reasons for that. Sometimes the plasma treater can't overcome those reasons. They're more endemic to the material than anything else. But nonetheless, it also can affect the longevity of a given dyne level and reduce its decay rate. Because we're ionizing a gas that we're bringing into the treater, we don't typically experience any reverse side treatment or treatment behind the web, backside treatment, because, well, there's no gas back there. So there's no process gas behind the web. We can't ionize it, and if we can't ionize it, then we don't get any negative from that. The ozone emissions that are generated from an atmospheric plasma treater are typically less than that of a corona treater, and there's a number of reasons for that. Generally speaking, plasma treaters tend to run at lower output voltages than a corona treater. So the high voltage side of a corona treater typically is in the 10,000 volt range. The high voltage side on an atmospheric plasma treater may be as little as 3,000 or 4,000 volts, but typically it's maybe 5,000, 6,000 volts. So it's lower in output voltage than a corona treater, which also helps explain why you don't get the little filaments that you see with a corona treater. But again, that in and of itself, if you just pluck that one detail out of there, it doesn't really mean anything relative to, oh, I'm going to get better treatment or anything like that. It really just means that depending on the substrate, that feature may be desired. The other benefit to these atmospheric plasma systems are that the chemistry can be changed. When you're turning your corona treater on, the air is what the air is. You can't change it. So, it ionizes the air that's there, and you're good. In a atmospheric plasma treater, if we typically run a gas combination, let's say is 95% argon and 5% oxygen, and we get a given result, and we change the substrate or we change something in our process, and now we made the change, and now the treatment isn't quite what you wanted. Well, let's say you reduce the argon by a few percentage points and you increase the oxygen a few percentage points. Well, now all of a sudden you went from a result that wasn't ideal to back to where you had a good result. you can't do that with a corona treater. So atmospheric plasma treaters do have some benefit relative to being able to vary the chemistry that's being used. And then the last two items here, again, the surface, the functionality of the film is unaffected. So even though we're running it through a plasma treater, I'm not changing the basic foundational function of the film. I'm just really working to decontaminate the very top layer, the very top area of that film substrate. Next slide. So what are some offsets here? What's not to like about a plasma system? Well, your initial capital costs are higher. Just by nature of the design, you have a lot more parts. There's a lot more things going on there to manage the gas and put it where you want it and all these various things. So the CapEx is going to be higher. Installation costs are going to be more because you not only have the treater, but now you have a gas control system. You have a tank farm somewhere. You also have continual replenishment of that gas. So you're going to have a truck pull up to your place, and you're going to either offload bottles or you're going to, have them top off a tank inside your place that where the gas is always being consumed. And of course, you don't have that with a corona treater. Depending on your line speed and substrate, there may be limitations there. So, for example, if you have a substrate that has a very, very, very textured type surface, maybe it's a little thicker, a textured surface, you may be limited in speed because as that material gets into the plasma, it might carry some of the gas away if you go too fast. Now, again, there are things you can do to mitigate some of that, but it is something to know and to discuss on the front end. It's something that when we talk about the overriding theme here of getting the application information together for you, that's one of the things when you talk about an atmospheric plasma treater. You kind of need to really know the details of the substrate, sort of your line speeds, and then make sure you work all that out. When you look at the physical size of a plasma treater versus a corona treater, they could be similar, but many times the atmospheric plasma treater, again, just due to the nature of the additional components and so forth, tend to require a bigger space. Now, it's not as though it's like twice the size or anything like that, but it is something that needs to be discussed and understood, on the front end of a project. Next slide. So lastly, we're going to touch on gas flame treaters, and really gas flame treaters have been around for a long time. They can be very effective tools when when used to treat low surface energy products. So let's dive in. Next slide. So to start with, a gas flame treater is really just what it sounds like. We take a combination of a percentage of natural gas or propane, but typically it's natural gas, and we combine that with room air. A typical ratio is 10 parts room air, 1 part natural gas. We apply that to a specifically designed burner. We light it, thereby creating a flame, and we aim that flame at a chilled roll, which then a web is conveyed over. And that web could be, a film web, it could be a paper web, could be board stock. There are a number of things. It can, the treatment profile of this, the end result of flame treatment can be very, very good, particularly as you're going at high line speeds. The higher the line speed, the more the economics work in favor of flame equipment. It can provide film substrates with very high treat levels. You don't have to worry about things like ozone, backside treatment, of course, no pinholes or anything like that. And it does a great job of decontaminating or cleaning the surface of various substrates. Next slide. So an offset, or some of the things to think about on a gas flame treater is, well, again, it's a fixed chemistry, right? It is what it is. When you turn it on, the flame's going to come out. It's going to be what it is. Yes, you can adjust the gap. You can adjust the power. You can increase the amount of air. You can increase the amount of gas a little bit. So meaning you can change the ratio as you need to. That may give you different end results. But at the end of the day, these are, relatively speaking, tighter controls that are available for you to play with. Speed limitations. So flame treaters do a good job when the web is moving, right? If you have an application where really you want to run 100 feet a minute or 50 feet a minute, or, you know, relatively low speed. Gas flame treaters really are kind of like the sledgehammer, if you will, of surface treaters. They produce a lot of BTUs. If you convert that into kilowatts, it's a big kilowatt number, and that power's got to go somewhere. And if the substrate is moving too slow, you really run the risk of damaging the substrate. That's really the thing. So as you go up in speed, gas flame treaters become very, 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 and a very effective tool of surface treatment. Installation costs, again, a bit more than the other two. Usually it's because you have a flame treater, usually is pretty good in size. Physically, it's a good size. It always has a water cooled roll, so there's ancillary equipment, you know, to support the roll. You have a hood over the flame treater itself to, you know, to contain and exhaust any heat and various byproducts that way from the gas flame. And then, of course, you've got a control cabinet that's located somewhere, and in that you have obviously your controls for the burner and safeties and all that, but then you also have mixing equipment and other devices in there that actually help combine the gas and air together to get it out to the treater station so you can create the flame. So it takes up some space. And then finally, you have to look at your local authorities and your insurance carriers and carrier's position on having an open flame in a plant setting. A number of times we've had discussions with folks about, hey, this job, you know, this application of flame treater would be good. They do some legwork on their end and they find, oh, you know, my local authority here is not looking friendly on having an open flame in the plant, or maybe it's their insurance carrier that says, hey, you know, we're not comfortable with that for various reasons. So it's just something to be aware of and to look at as you go forward if you're considering, or if your application really is commensurate with a flame treater. Next slide. So flame treaters today, this is really an important thing to know. Some of you may have flame equipment that's been out there for 20 and 30 years, and while it actually still operates, you've learned over the course of time that it's probably not at its optimum, right? So what's changed? If you look at your existing asset that's sitting there, the flame treater that's sitting there, and you looked at getting a new one, what really has happened here relative to improvements in the general basic technology? Well, they're really two main things, right? One is, and probably the most important, or one of the most important, is going to be the design of the burner. Burners today are not designed as a crimped ribbon burner anymore. Now, that technology is that crimped ribbon technology is the same stuff that you see in your gas burner in your yard, or maybe in your oven, and it's still very effective for certain applications. So if you're making burner technology that's being used in those applications, then that is a very cost-effective and highly effective way of going. Not the greatest for film, right? In a film application, I need a burner that I can get some control with, that I can control the flame geometry, I can control the flow of the gas, I can get the geometry of the flame to be just what I want, how I want, as it's presented to the film. And if I can do that, the film is going to benefit by being treated more uniformly, less problem with the film, less wrinkling, less trouble, for lack of a better way of saying it, than if I, have this sort of crude method of generating a gas flame. And then the second half of that all goes back to the control scheme. So back in the day, the control schemes sometimes were really simplistic. It had a couple of hand knobs on it, maybe a sight glass or two, and your operator was expected to go over there and sort of match things as best they could and try to get the mixture of gas to air to be acceptable enough to treat something. And sometimes it worked very well. Other times it was either too rich or too lean. That then caused a bunch of problems, some of which you may not even recognize until your product was shipped to a customer, or maybe you were trying to convert it yourself. So the burner design and the control of that burner design and the mixture ratio and the way the gas is handled and managed, altogether different today and much better. miles and miles better than the equipment that was used some 20 or 30 years ago. Now, when you compare a flame treater cost to a corona and atmospheric plasma treater, yeah, I mean, they're really, again, apples and oranges sorts of comparisons, right? Typically, a flame treater is used in things like extrusion coating and extrusion laminating lines that are running maybe thousands of feet a minute, 2,000 or 3,000 feet a minute. Maybe in wide BOPP lines that again are running, 500-600 meters per minute. Those applications, because of their speed and the product, they require a lot of power. And so a flame treater delivers that in the most effective and efficient manner. It's not that corona or atmospheric plasma couldn't technically do it, but because of the amount of power that's required, they would be really oversized. They'd be huge. Your expense and the trying to locate them and everything would just be outrageous. And so really, again, the application details, your material, your speed, all those things, they really, really do drive, which technology we look at for you. Next slide. So in converting applications, as an example, most people use some sort of ceramic electrode and ceramic coated roll for printing, coating, and laminating applications. They tend to be the best. When you're dealing with high-speed converting applications, cast film, extrusion coating, laminating, things of that nature, you will note that many times gas flame may be used there, maybe in combination with corona. We've had applications where we actually have corona, gas flame, and ozone generation, which we didn't get into in this topic, but that are actually kind of combined in a system in order to go ahead and do the job. Difficult to treat and engineered type materials, typically those applications gravitate towards plasma. So an example there might be, you have some fluoropolymer you're trying to functionalize, you're trying to get something to stick to a substrate that really, its original intention was for nothing to stick to it. In those instances, many times plasma treaters can be quite effective in getting you to that next stage in your process. So again, the material, the application, what you're doing, speeds and so on, all those things sort of get rolled together, and that's what really helps us, guide you into the right piece of the correct design, the correct engineered piece of equipment for your particular application. So it really, as I said to start in our presentation today, there really is no best type of corona treater. It really depends on what application and the details of your application going forward. Next slide. In extrusion applications, you'll see that, as we said in our presentation, covered roll treaters, stainless steel electrodes, things of that nature, blown film, cast film, they can be really used a lot in that application. If you're going to do high speed, wide web type of things, again, maybe the flame treater is something to consider there. And again, for more esoteric or highly engineered films, you might look at a plasma system. So really, what do we learn from all this today? I did a lot of talking and told you a lot of things, but really the takeaway from all this is there is no best surface treatment technology. It really depends on your particular application considerations. And then, as Mark said when he opened the presentation today, if there's doubt, if you really can't wrap your mind around all these choices, the best thing then is to run samples on all three technologies. As a sort of final promoter for Enercon, we are the only one here in the country that can operate these three systems in our lab. We have a gas flame system, 2 atmospheric plasma treaters, 2 versions of atmospheric plasma, and of course a corona treater that can be made into any version of corona treaters. As we said in our presentation today, there's multiple types of corona treaters. And so if there is a question in your mind about, well, what about this or what about that, run a sample. I mean, that's really the best way to kind of come up with a solid answer and give you some confidence going forward.
All right, thanks, Tom. And Tom, just to check, can you hear me?
Yes, I can hear you, Mark.
Oh, okay, good. I had a phone issue for a moment. So we're going to get to questions, and the first question is, you mentioned there could be an instance where the dyne value can revert after a certain amount of time after treatment. Would this mean that the coatings that have been applied could come undone?
That's a great question. Typically not. Typically, when the coating is applied and it passed an initial peel adhesion test, typically that's good. Remember, the dyne number here, the dyne value doesn't reflect anchorage, right? Dyne numbers and the measurement of a dyne is strictly measuring the surface tension of the web's ability to wet a liquid. We're just looking for a wetting characteristic. So it doesn't really affect, adhesion going forward. Now, if that's a problem, if you have that experience, there are things to check. Certainly from a corona treater or a surface treater standpoint, you go back through your data and you say, hey, was the treater even on? Was it on at the right number? What speed were we running? There's a long list of stuff you can check there. But just in a general answer to your question, typically no. Once the material is coated or printed or laminated, you're pretty good unless there's something else that happened with the substrate.
All right. We have two people that were just asking about our technologies for non-roll-to-roll applications. And what I can tell you is actually next Thursday, we'll be holding a webinar on our flame and plasma technologies for that. If you're interested in treatment solutions for things that are not film roll-to-roll, send us an email and we'll get you some credentials to register for that webinar next week. It's going to include some videos of equipment in operation, and we'll be happy to share what we know on those topics as well. Next question, Tom, is, are the flame treater exhausts similar to typical dryer oven emission in a plant?
I would think they're similar. Now, I'm certainly no expert on, press dryers or coating dryers or anything, but I've been in enough plants to understand that there are some similarities there. Typically, the exhaust for a flame burner is really comprised of a big hood, sort of like a hood exhaust hood you'd see in an extrusion coating line, where you have this big hood that's over the extruder and it's sucking up the various contaminants from the extrusion process. It's of a similar nature in a gas flame system, maybe not quite as large, but from a picture in your mind kind of thing, it has some similarities, yes.
Question on if there's a significant amount of film distortion when using flame treating versus corona or plasma.
Well, there shouldn't be. If you're getting wrinkling, if wrinkling is occurring because as the web's going through the flame treater, that can be for a number of reasons, and I don't need to dive into every one of those reasons. But if the burner's adjusted properly, if the roll's being cooled properly, the material's being conveyed in a manner that's commensurate with using a flame treater, then you really shouldn't experience any sort of distortion or wrinkling or melting or anything negative relative to the use of a flame treater.
Tom, typically, how long does corona treatment last on a film if it is rolled up?
Well, it really depends on the film. So I'll give you to illustrate the point, I'll give you two really vast examples. So you could take a piece of polyester film, corona treat it at a given watt density, and derive a dyne level of, say, 50. Okay, so we went from a dyne level of 40 untreated to a dyne level of 50 using a given watt density. Now I'll take the same width film, but it's a polypropylene that started more like 34 dynes. I use the same power output, so the same watt density, but my end result is not 50, my end result is more like 40. And in both cases over time, you'll see that typically the polypropylene film that dyne level decay is going to be more aggressive than the dyne level decay in the polyester. Even though both were treated with Corona, both were treated at the same watt density. And the reason for that is really simply the structure of the film itself. The propylenes tend to have additives then that come to the surface. Their surface becomes more crystalline over time. That can affect the dyne level going forward. Wherein the polyesters tends to be more stable. Surface of it is more stable. And so when you treat it to a given dyne number, it can decay, or it does decay, but the decay rate is smaller and slower than typically you would find in a polypropylene film. So really, it really is depending a lot on the structure, the film structure. What is it? What's in it? How tight do you wind it? How do you store it? There's a lot of moving pieces in what seemingly seems like a simple question. there's a lot of things to consider there.
Tom, what would be the best or most common type of treatment technology to enable digital printing?
Yeah, I mean, the one that's used to this day most frequently for that application is Corona treating. Corona treating tends to be the default there. A number of reasons for that, but by and large, the reasons can be suitable just by saying economics and physical size. Most digital machine presses are fairly compact. The Corona treaters that are used for those need to be compact in order for them to fit. Just the general nature of Corona being what it is, it's pretty universal. The equipment is widely used. It's widely known. Economically, it's, as compared to everything else, it's going to be less expensive. So typically for that application, you'd gravitate towards a Corona treater.
All right. This customer works a lot with EPDM and UHMP. What would be the best treatment for these types of materials? And further, is there such a thing as a portable unit that can be used for demo purposes?
Well, I'll take the last part of it first. I don't have a portable, or I'm not aware of a portable roll-to-roll Corona treater. As you can imagine, if this is a roll-to-roll application, it would be a bit difficult to install all this equipment somewhere to do an on-site test. Now, we can treat the substrates you mentioned in our lab, and once we're past the COVID that we have today, and prior to COVID, of course, we had people visit with the lab, and they would watch our material run through these various technologies, Corona flame, whatever it was. So, at some point, certainly today, we can still run samples for you. The visiting part's a challenge at the moment. That'll change. But certainly, if you want to run samples of your two products and then gather that data and get to an understanding of how surface treatment works for those two, I can tell you that on substrates like EPDM, where it's essentially a rubber and it's essentially an insulator, right? So the answer is in the details here, and that I'm not going to be able to get into at this depth at this conversation. So if the individual asks the question, if they want to send me an email on the side, or call me sometime and get to the details, I'll be happy to talk to them about that and with greater information.
Okay. Other than ozone generation, what other safety considerations are there when using Corona? Example, employee exposure, et cetera.
Well, there's no damage to employee just by walking past the Corona treater or looking at it. It's not going to hurt you. It will not affect you at all. Now, if an employee would go up to an operating Corona treater and stick their hand in there, the potential then would be for an electric shock to occur. Now, all Corona treater manufacturers make equipment today that have varied and numerous safety devices around them that could preclude that from happening. But at the same time, as I say that, I can tell you that people will do the darndest things, right? People do some things that sometimes you have to scratch your head and say, I wonder why they did that. And so it is, you have to be mindful around corona treaters that are operating. You certainly don't want to stick your finger in there, just like you wouldn't want to stick your finger into a machine with a moving web. It's really all the same in that regard. You just have to have, safety guards in place, rules and procedures, safety policies that are followed. Really no greater or no more so than on any other piece of gear on a converting or film extrusion line that you have today.
Let's see. Tom, how can you tell if an ozone catalyst has degraded?
Well, one of the best ways of doing that is when you install your decomposer, you drill a hole in the pipe in the ductwork before the decomposer, and then you drill a hole in ductwork after the decomposer, and you put a plug in there. Over the course of time, you measure the amount of ozone on either end. So, before the decomposer, you take a measurement. After the decomposer, you take a measurement. And you continue to record these two values over time. And you should see over time that the value after the decomposer will become less and less effective. So if you start off at 99.9% efficient at removing ozone, just the way the system operates, over time, you will see the efficiency slowly drop off. And at some point, the value that you measure after the decomposer is going to get to a point where you say, oh, I'm not happy with this value anymore. I need to take an action. Typically, the action is simple. It just means you have to add more catalyst. The catalyst in these beds look like, if you haven't seen it, they look like little BBs. And as that large amount of air volume goes through that bed, they rattle, they move around. And as they move around, they will ultimately, over time, become smaller and smaller and smaller. And as they become smaller, the dwell time of the ozone inside that bed is reduced, thereby causing a lower efficiency. And so when it gets to a point where you're not happy, you then just go ahead and top the catalyst off, and you should be good to go. Regular maintenance on these is really no more than what you typically find at that you normally do now. You take the filter out every month or check the filter every so often, and the pre-filter gets checked, put a clean one in, you're good there. And then you just visually inspect the pre-catalyst, the alumina pellets that are here, and then just make sure they're all fine, that they're still there where they belong, and then you're good. There isn't really much else to do. The unit is pretty simple. It's basically a standalone unit, doesn't have any utility to it. It's not powered by anything. So it's a relatively simple device to maintain and to take care of.
All right, we are running over on time. We're going to try to get to a few more questions here. Tom, is it possible to create a comparative table of contact angle versus treatment levels? Is it a good and realistic experiment?
Well, practically speaking, you can do it. We did it. We did it in the lab for quite a number of years. I think probably 2 years. It might have been a little more than that, actually, now that I think about it. We were hopeful that we could get a contact angle number to be a drop dead replication or direct connection to a dyne number, because as everybody knows who's done dyne testing, that test method has a number of flaws to it, just that are baked into the method. And of course, if there were something different to use, people would gravitate to it. Unfortunately, the contact angle method, while very beneficial in terms of measuring the surface's ability to wet a droplet, doesn't translate, practically speaking, very well over to a 60-inch moving web. So what I've recommended people do is, do your dyne test as you normally do, record that data. If you want to do a contact angle, make another column that says, okay, here's the contact angle before we treated, here are the various contact angles after treatment, record that data. Then record your peel adhesion numbers. Let's say you're printing or coating or something. Record that data, and then basically keep records of that in that sort of order, and keep a record of what the power was at each one of those stages as well. And over time, you'll develop some really, really solid data that really will only be used if you have a problem, right? You'll never really tap into that data unless you have a customer that comes back to you and says, I had a failure. I had an issue that, that the end result was I'm not happy about, and I want to figure out why it happened. And then you're going to go back to your data and look at all these various values, and you're going to look for an outlier. You're going to look at something that says, hey, wait a minute, how is it that at this date with this job, our normal numbers were looked this way, but now we don't? Now the contact angle number is off, or the dyne number is off, or the peel adhesion number is quite not right. So that's really the benefit of doing it. There is really no direct comparison that say, well, on every film, a contact angle of 40 equals a dyne level of, 60. It just doesn't really work that way.
Tom, what's a typical treater for a cast film extrusion line that runs at speeds around 200 feet per minute?
Typically, well, it depends on the width, but typically, if I just picked a very typical application, you'd have a fixed width electrode of some sort. It could be a metal electrode, it could be a ceramic electrode. It just depends on really what material you're casting. Is it a OPP? Is it a BOPP? Is it a slip modified film? Is it, what is it? And then, based on what the details are and sort of what you're looking to accomplish, we would then, tighten that down and recommend the right corona treater for it.
I've got an application question. We have someone here that treated some PVC sheets with a bare roll corona system. They've lost ink adhesion on the treated face and bonding, hot lamination, on the untreated face. Any indications of what could possibly be the cause of this?
Well, the question, I hate to answer a question with a question, but you got to go back and look at the construction of the PVC. So PVCs generally come in a couple of variations, right? And again, I'll give you two extremes. So on one extreme, you have PVC that's more akin to the consistency of a shower curtain. And on the other extreme, you have a PVC that has more of the consistency of a credit card. And so as you can imagine, if you think of those two things in your head, the treatment and the resulting treatment of those two things are vastly different. So in the case of a rigid PVC, where there's not a lot of additive in there, treatment is pretty straightforward. The treatment level tends to maintain itself. In the other extreme, where the PVC is more akin to like a shower curtain, you find that product is going to be a lot harder to treat. And when you do treat it, the treatment may not be stable. It may not last a long time. So again, the details matter in a question like that. You really need to understand, the details of the particulars of the product that, that was being treated.
Okay, we've got a question in two from the same person, so I'll combine them. Dyne decay of OPP film, does it depend on the surface treating method as far as the rate of decay? And under the same dyne level after treatment of polypropylene film, what is the difference in the surface chemical composition, if any, between corona, flame, and plasma? Is there any difference in oxidation?
Well, relative to the question about dyne level decay, we do know from testing that, for example, a flame-treated surface on OPP, generally speaking, will have a shallower decay rate. So it's not uncommon to see a BOPP film that's been flame-treated, see that decay rate. It still decays, but it may decay at a slower rate than, say, a corona-treated sample. Okay. Now, again, I can't give you the answer you're looking for, which might be, well, this happens all the time. Because I can equally tell you, we've seen polypropylene samples where they were treated with a gas flame system and the decay rate was, wasn't great. It was maybe not quite as aggressive as a corona, but it was still pretty aggressive. So the devil is in the details of the material. Keep in mind something, folks. The corona treater, gas flame treater, plasma treater, they're just treating the surface of this product. So they're only going a few angstroms deep. How that product was created, the additives that are in it, the extruder temperature, the winding tension, the environment the film was kept in after it was made, the cooling. If it's a blown film, what was the bubble cooling like? What's the cooling method in the OPP line? How do they control it? Is it tightly controlled? Was it not operating properly at the time? All those various things, they may sound incidental to you or not connected, but believe it or not, and when you're talking about surface treatment, they can all be connected. And that's the hardest part here when we have these questions about things like the dyne level, because while we can manage what we can do, meaning we can manage the treater, gas flame, plasma, corona, I can turn the power up, I can increase the gas rate on the flame treater, I can change gas chemistries in the plasma treater, and all that's fine. And you might see an incremental benefit. But at the same time, you may also still see a decay that you're not happy about. And that largely is as a result of the construction of the substrate itself. So, there's a context or contextual component to this question that you really need to understand.
All right, thanks, Tom. I'd like to thank our audience too. If we didn't get a chance to answer your question, we will reach out to you after the webinar. Also, feel free to reach directly out to Tom. You've got his email and phone number there on the screen. If you liked the webinar today and found it informative, please drop us a line and let us know. If you have ideas for future topics you'd like us to cover, please do that as well. Again, thank you for attending today's webinar, and we will send out a link to the recording of this for everyone tomorrow. Thanks and have a great day.